Now we're going to talk about Young's double slit experiment, which is a classic experiment that we use to study the light transmitted through a double slit. Okay, so this Young's double slit experiment, the word Young's actually referring to the person who devised this experiment, which is Thomas Young. So it's designed by Thomas Young to study the interference of two light waves, basically. Okay, so how does Young's double slit experiment looks like? You have a single slit first, even though it's double slit experiment, but it start with a single slit, in which we are going to call this single slit here as slit 0 or source 0. So you're going to place a light source over here, and you have light transmitted through this single slit over here, or you can think of it as a single poke of a hole through an opaque board. So light cannot transmit through the board, light can only transmit through this slit over here. Then the light will transmit out from this slit 0 in a circular manner. Because this is a very small pinhole, you can expect that the light that emerge from this slit here to be a 2D circular wave, or in 3D it will be a spherical wave. Okay, so the light will continue to travel to the right until it reaches another board which is arranged parallel to the first board. Again, this second board over here is also opaque, but we've poked two holes through this board over here. So light cannot pass through the opaque region, light can only pass through these two slits over here. So you have light emerging from slit 1, you have light emerging from slit 2, and they happen simultaneously, they happen concurrently. So in that case, you can see that there will be two light waves coming out from these two slits, and they are going to overlap in the same region over here. And because they overlap, you know that the phenomena of interference will occur. So we are going to study the pattern due to this interference later on. Okay, here I'm drawing two waves to be green color and blue color. It doesn't mean that the light emerged from slit 1 is a green color wave, it's a green color light. The light emerged from source 2 is a blue color light. That is not true. I'm using different color just to differentiate that the green color is the light emerging from source 1, whereas the blue color will be the light emerging from source 2. It doesn't represent the actual color of the light itself. In fact, the color of the light that emerged from source 1 and source 2 should have the same color, and we'll study the reason why. But here I'm just trying to emphasize that I use two different colors just to differentiate that they emerge from different slits over here. Okay, so now let's try to discuss the requirement that you need to achieve in order to have a clear and stable interference pattern. So to obtain clear and stable interference pattern, the setup should achieve two main requirements. So the first most important requirement is that your two light source, which is light coming out from source 1 and light coming out from source 2, the two light source has to be coherent. Okay, what do we mean by coherent? Well, in English you can say you make a coherent sentence that makes sense, or a coherent essay, a very well structured essay, something like that. But in physics, or in particular when we talk about wave, the word coherent has a very specific meaning. Okay, here I think I split coherent to be in we talk about coherence in two main elements over here. So I can say coherence has two main elements. First element is that it has to be a monochromatic light of same frequency. So if I tell you S1 and S2 are two coherent light source, these two lights that emerge from these two light source has to be monochromatic light of the same frequency. Mono means one, chromatic means color. So one color light. So the light that comes out from source 1 and the light coming out from source 2, they have to be the same color, one color only. So one color, in terms of physics, color is determined by the wavelength of the light wave. So if you have one single color only, that means you have only one single wavelength. Okay, so this actually means single wavelength light. Single wavelength light of the same frequency, so single wavelength, single frequency. So you can think of it as the light wave emerging from slit 1 and slit 2, they should have the same wavelength, same frequency. That's the first element of coherent. The second element that we are going to talk about is constant phase relationship. If you want to call these two light waves to be coherent, these two light waves will have to have constant phase relationship. So a rough idea is, if the light emerging from source 1 right now is a crest, the light emerging from source 2 is a crest, then they are in phase, right? So later on, if they are trough coming out, crest coming out, trough coming out, crest coming out, then the light that is emerging from slit 1 and slit 2, they are in phase, right? In this case, it is valid to call them to have a constant phase relationship. Okay, also it can be light coming out from source 1 to be crest, light coming out from source 2 to be trough. That one also can be called as constant phase relationship, as long as if one becomes trough, another becomes crest, and when it can become crest, the other one will become trough. If they are constantly opposite phase of each other, or we can call it as anti-phase, if they are constantly anti-phase, that is also valid to be called as constant phase relationship. Okay, the idea might be a bit blurry to you right now, but later on I'll describe it in greater detail. Okay, but for now you can know that coherence has two main elements in it: single wavelength, single frequency, and constant phase relationship. I'll discuss the idea in greater detail just a little bit after this. Okay, the second requirement for you to have a clear and stable interference pattern is to have same amplitude for both light source. So these two light sources here should have the same brightness when they emerge out from these two slits. So yeah, same amplitude, same brightness. That's the main idea. Okay, but now let's focus on the idea of two coherent light source, and we are going to go through these two elements here in greater detail. So the two coherent light source, the first element is it has to be monochromatic light of the same frequency. Mono means single, chromatic means color. So single color, in terms of physics, color is represented by the wavelength of the light, or is controlled, or is determined by the wavelength of the light. So if you want one color only, it can only have it has to be based on a single wavelength only. Okay, this word is a bit misleading, but I didn't think I want to explain further about it. Okay, white color has a lot of wavelength in it, but the idea of monochromatic here in physics, even though you translate as single color, but the actual meaning of monochromatic is they want single wavelength. Okay, so single wavelength, same frequency, single frequency. So single wavelength, single frequency. That's the idea of coherent light sources. So let's say if you have source 1 and source 2, then the light emerging from source 1 is like this, the light emerging from source 2 is like this. Then we can call it as monochromatic. Why monochromatic? Because source 1, the wavelength is the same as source 2. They both have the same wavelength, so your idea of single wavelength is achieved. Single frequency is also achieved if they're traveling at the same speed, which is all the time. Okay, you have single wavelength, single frequency. Here, an idea of what is not monochromatic is something like this. If you see source 1 have a shorter wavelength, a greater frequency maybe. Okay, source 2 have a greater wavelength. So in this case, the wavelength is different between source 1 and source 2. This is not monochromatic at all. Okay, another way of thinking of not monochromatic, non-monochromatic light is this one. You can see that even though they look exactly the same, they are in phase with each other, they are not monochromatic. Why are they not monochromatic? Because this kind of wave is actually wave that is made out of a combination of wavelength. Okay, if you have light wave made out of a single wavelength, the light wave should appear in the sinusoidal shape. But if you combine multiple wavelength, let's say you have shorter wavelength combined with longer wavelength, let's say blue light combined with red light. Okay, blue light shorter wavelength, red light longer wavelength. If they combine with each other, what happens is the two light wave will overlap each other, then you result in waves that are a bit irregular in terms of its shape. Okay, or yeah, if you see waves that are not pure sinusoidal wave, then those waves are actually made of combination of wavelength. So if they are combination of wavelength, that means it's not single wavelength. So this kind of situation, this is also not a monochromatic wave. Okay, so if you want two coherent light source, your two light source should have pure sinusoidal wave emerging from it, and they should be having the same wavelength. Okay, so that's the idea of the first element of coherence, which is monochromatic light of the same frequency. The second element is that you need to have constant phase relationship. Phase relationship doesn't mean in phase. Phase relationship means by who is lagging, who is leading. That kind of relationship has to remain constant throughout the experiment. Okay, the most simple kind of phase relationship is in phase. Okay, that's the easiest to understand kind of phase relationship, in which you have source 1 and source 2. The light wave that emerge from it, if it's equilibrium, it's equilibrium for another source as well. If it's crest for another source as well. If it's trough for another source as well. So they're emerging out with the same rhythm, same pace, yeah, same phase. Okay, so you can see that right now emerging out from source 1 and source 2 is equilibrium, then it's trough, crest, 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 trough, crest. Okay, the idea is if it's trough coming out for source 1, it's also trough coming out from source 2. If it's crest coming out from source 1, it's also crest coming out from source 2. So you can see that it's crest, crest, trough, trough, crest, crest, trough, trough, crest, crest, trough, trough. So this kind of situation, we call it as in phase with each other. So the relationship between source 1 and source 2 is they are both in phase. The phase difference is 0. Okay, so this kind of situation is a constant phase relationship, correct? But not because they are in phase, but because they are in phase all the time. That's the main idea. That's the meaning of constant phase relationship. It's not because they are in phase, but they are in phase throughout the experiment. Then it's constant phase relationship. Okay, you can also have different kind of constant phase relationship. So let's say today, I have two light source again, but this one, when trough is emerging for the another source, it's crest emerging. When it's crest emerging for source 1, it's trough emerging for source 2. So this kind of situation, they are not in phase at all. Technically, they are anti-phase, and the phase difference or the phase relationship is maybe source 2 is leading source 1 by pi radian. Okay, the phase difference is pi radian, or it's 180-degree phase difference. But it can still be called to be having a constant phase relationship if this pi radian phase relationship remains throughout the experiment. Okay, so let's see whether it's in phase, let's see whether they are having constant phase relationship or not. So now you see it's crest, then it's trough for another source. Then if you let the wave travels throughout the experiment, you can see that the relationship is maintained. It's always, if crest come out from source 1, it's trough coming out from source 2. If it's trough coming out from source 1, it's crest coming out from source 2. This relationship of trough, crest, crest, trough, trough, crest, crest, trough remains throughout the experiment. Even at earlier time, it's crest, trough, trough, crest. At later time, it's also crest, trough, trough, crest. The relationship is maintained throughout the experiment. Even though it is not in phase, it is anti-phase, but this anti-phase relationship remains throughout the experiment. It doesn't change from in phase to anti-phase, back to in phase, back to anti-phase. It doesn't change throughout the experiment. So in that case, we can also call this situation here to have constant phase relationship. Okay, now let's give an example why it's not a constant phase relationship. So right now you can see that they are in phase. So you might be thinking, oh, maybe this one has constant phase relationship. But no, the idea is if it is in phase, it has to be in phase throughout the experiment. Then it only is valid to be called as constant phase relationship. So let's see whether this is constant phase relationship throughout the experiment or not. So you can see the wave is traveling. They looks like they are in phase each other throughout the journey. Oh, but there's a kink over here. Now you can see that the relationship changed. Another kink over here, the relationship changed. Another kink over here, the relationship changed. Right now you see that they are nearly in phase, not exactly in phase, but they're nearly in phase with each other. But when you reach this point, they are nearly anti-phase with each other. Then here they are nearly in phase. Here they are even more in phase. So you can see that sometimes they are in phase, sometimes they are out of phase, sometimes they are back in phase, sometimes they are slightly in phase. So the relationship keep on changing throughout the journey of the light wave, or throughout the experiment. The relationship change from in phase, out of phase, go in phase, go out of phase. If it's changing throughout the experiment, then the phase relationship is not constant. So in that case, we can say source 1 and source 2, they are not coherent with each other. Okay, so now to summarize it, in order to have a stable Young's double slit experiment pattern, in order to have a stable pattern, you need to achieve two requirements. One is you have to have two coherent light source, Another one, you have to have same amplitude of light emerging from the two light source. Okay, coherence is made of two different elements. So there are two elements you need to achieve to have coherent light sources. One is it has to be single wavelength, single frequency. Another one, it has to have constant relationship. Okay, so two requirement. For the coherent requirement, there's two elements. Okay, for another requirement, same amplitude, that one is just the least important kind of requirement. Okay, so just to recall, how do we achieve these two requirements in the Young's double slit experiment? So first you have a single slit over here, then you place your light source over here, right? So right now, because light can only pass through this single slit, we call it a slit 0 over here. So the light will emerge from this single slit here in a circular 2D wave or a spherical 3D wave. Now, if you place a parallel opaque board parallel to the first board, and you poke two holes through this board over here, you have slit 1 and slit 2. Now, this simple idea, this simple setup of having a single slit first, followed by a double slit, actually is the method that Thomas Young used in order to achieve the two requirements. So let's try to recall the two requirements. The first requirement is to be coherent. Means that source 1 and source 2 need to be coherent each other. They have to have single wavelength, single frequency, which is easily achieved because they come from the same slit, and this slit only has one light source passing through it. So if it's a yellow color sodium lamp, then the light wave that passing through the slit 0 will have a yellow color wavelength, single frequency. Then when you reach source 1, when you reach source 2, the color doesn't change. It is still the same yellow color. So it is still the same wavelength that come out from source 1. It is still the same yellow color coming out from source 2. So easily you can achieve the first element of coherence, which is single wavelength, single wavelength, single frequency. The second element, which is constant phase relationship, how is it achieved by this simple setup over here? Well, if you think about it, if you start with a single slit over here, the light wave that emerge from this slit over here, we have to travel a certain distance to reach slit 1. You also need to travel a certain distance to reach slit 2, right? So now if you arrange it in the way that the distance from slit 0 to slit 1 is the same as the distance from slit 0 to slit 2, or you can think of it as equidistance, this distance and this distance here, if they are equidistant, then if the light wave arrives at source 1 or slit 1 with a crest, technically the same thing will happen for the light wave that arrives at slit 2. It will also arrive at the crest because they travel the same amount of distance. If it's peak, trough, peak, trough, peak, trough, peak, trough, then of course the same thing will happen for the journey to slit 2. It will go from peak, trough, peak, trough, peak, trough, peak, trough. So both of these slit will receive the same trough at the same time. Then later on it will be peak, later on it will be trough, later on it will be peak. So the light waves that arrive at both slits, they are in phase. So the light that emerge out from slit 1 and slit 2, they should also be in phase. And in order to make sure it's constant relationship, we have to make sure it is in phase all the time, right? Well, this can be easily achieved because these two slits, even though you see them as two light source, the two light source actually originates from the same single light source. So if you emerge coming out from this same single light source, you can easily ensure a constant phase relationship. Because let's say if the light suddenly flickers over here, it will maybe dims and come back to be bright, right? So when it flickers, what happens is source 1 will flickers together with source 2 at the same time, because the light that travels from source 0 to source 1 and the light that travels from source 0 to source 2, they are the same distance. So source 1 and source 2 will flickers at the same time. They went off at the same time. They'll start back at the crest at the same time. They'll start back at the trough at the same time throughout the whole experiment. No matter what kind of changes that happens to the light source in front, the changes will affect both source 1 and source 2 simultaneously. So even though initially it is crash, then suddenly it become trough, the effect will follow for S1 and S2 as well. Okay, so the phase relationship will remain throughout the experiment, because no matter what happens at the light source, the effect will be propagated to source 1 and source 2 simultaneously. Okay, so it won't go out of phase because they come from the same single point light source. Okay, so that's how you maintain the constant phase relationship, and that two elements is achieved, so therefore your source 1 and source 2 here are two coherent light source. So that's the first requirement achieved. The second requirement is to have same amplitude. Well, if the distance from these two slits are the same, your light that emerged in source 1, your light that emerged from source 1 and your light that emerged from source 2, they should have the same brightness, right? So same brightness, technically the second requirement is easily achieved. So just by having a single slit first coming before the double slit, you easily achieve the two requirements that we said just now on coherence and same amplitude. Now this is the way that Thomas Young devised in order to study the interference pattern of two light waves. Okay, of course the two light wave, of course the yellow lamp will not emerge out like this because this is an opaque surface, right? So your light will get blocked out over here. Light will only emerge from slit 1 and slit 2. So you can think of it something like this. You have light coming out from slit 1 and light coming out from slit 2. They are still both two yellow lights. I'm drawing here as green light wave and blue light wave, not to say that they are green color light and blue color light. They are both yellow light that emerge from slit 1 and slit 2. And green color here just represent it comes out from slit 1. Blue color here just to represent it comes out from slit 2. But because now we have two spherical light wave or two circular light wave overlapping in the same region here, what happens is the phenomena of interference will occur. So phenomena of interference occur right now. We can find certain points where we will see that it will always be crest meets crest, trough meets trough, crest meets crest, trough meets trough. Those kind of points will have constructive interference. So other points you will see it's always crest meet trough, trough meet crest. Those kind of points you will see destructive interference happen. So it all you can find certain points that are destructive, you can find certain points that are constructive, but we'll leave that to the next video to study the constructive and destructive interference, and from there we understand the pattern that will be formed through this interference.